Hi guys, today we'll be solving the AS Biology practical paper of October-November 2024, variant 4. The first question says, vegetables such as carrots contain sugars. Potassium manganate 7 solution can be used to identify the presence of sugars. The sugars change the color of the potassium manganate 7 solution from purple to colorless. You will measure the time taken for potassium manganate 7 solution to turn colorless with sugar solutions of known concentration. You will use the results to estimate the concentration of sugars in a carrot extract. You are provided with the materials shown in table 1.1. The materials are S, which is 1.0 mole decimeter to the power of -3 sugar solution, and W, which is distilled water. A is sulfuric acid, K is potassium manganate 7 solution, and C is carrot extract. If any solutions comes into contact with your skin, wash off immediately with cold water. It's recommended that you wear suitable eye protection and wear gloves to protect your hands when using A and K. You will need to prepare different concentrations of sugar solution. Record the time for K to become colorless, which is the endpoint for each of the different concentrations of sugar solution and the carrot extract. Use your results to estimate the concentration of sugars in the carrot extract. You will need to use proportional dilution to make 5 different concentrations of sugar solution. So you need to make 5 different concentrations. You will need to prepare 10 centimeter cubed of each concentration using S and W. Table 1.2 shows 2 of the concentrations of sugar solution you will use and how to prepare them. Decide which 3 other concentrations of sugar solutions you will use. So this is table 1.2. They have already given us 1.0 mole decimeter to the power of -3 concentration and 0 concentration. The volume of C is 10 centimeter cubed and volume of W is 0 centimeter cubed for 1. We need to create 5, so we can just minus 0.25 from each one, so you'll get the concentration of 0.75 and 0.5 and 0.25. And the volume, to find the volume of S, just multiply 10 by 0.75, so you'll get 7.5, and 10 times 0.5 is 5, to 1 decimal place, so 5.0, then 0.25 times 10 is 2.5, and then add distilled water, so that both of them will add to 10 centimeter cubed, 2.5, 5.0 again, and then 7.5 distilled water. Then carry out step 1 to step 11. Step 1 in the beakers provided, prepare the concentrations of sugar solution as shown in table 1.2. Label the test tubes with the concentrations of sugar solution prepared in step 1. Put 1 centimeter cubed of 1.0 mole decimeter to the power of -3 sugar solution into the appropriately labeled test tube. Repeat step 3 with each of the other concentrations of sugar solution. Then put 1 centimeter cubed of A into each of the test tubes. Shake gently to mix. The reaction will start as soon as you put K into the test tubes, so keep the timer running continuously until the end of step 7. Put 1 centimeter cubed of K into each of the test tubes and start timing. Shake gently to mix. Measure the time taken for each concentration to reach the end point. As each endpoint is reached, record the time taken in AII. If an endpoint has not been reached after 600 seconds, record the time as more than 600. So then, to draw the table, of course with a ruler, the table will contain 2 columns, and of course the row for the heading, and then we used 5 concentrations, so add 5 more rows. So the heading, on the left side, the independent variable, which is the concentration of sugar solution, and don't forget the units, which is mole decimeter to the power 3. And the dependent variable will be the time taken, and the unit, which is seconds. Then in the left column, just add the 5 concentrations. Then of course, the trend will be, if the concentration of sugar is higher, then it will take less seconds to reach the end point. And if the concentration is decreasing, then the time taken to reach the end point will increase. So for example, 1.0 concentration will take 100 seconds. The stopwatch will give you 1 minute and 40 seconds. But you can't write that. You have to convert it into seconds. 1 minute is 60 seconds plus 40, which is 100. Then the trend will be increasing time. So for example, 300. And of course, for the 0% concentration, there won't be any change in color. The potassium manganate won't become colorless. So this, of course, you have to write more than 600 seconds as it's given to you in the steps. Then label a test tube C and put 1 centimeter cubed of C into this test tube. Put 1 centimeter cubed of A into the test tube, shake gently to mix. Put 1 centimeter cubed of K into the test tube and start timing, shake gently to mix. Measure the time taken to reach the end point, record the time taken in AIII. After using C, for example, you will get the time taken as 400 seconds. And don't forget to write the units here as well, because you might lose a mark. And to estimate the concentration, you'll go back to your table. 400 seconds is here, so the concentration is 0.5. And the unit is given to you here, so you don't have to write it. For question V, suggest how the procedure could be modified to improve the accuracy of your estimate in AIV. So the concentration. Of course, the endpoint is a change in color, so it's subjective. So to make it more accurate, you can use a colorimeter, then it's a 3-mark question. So when using different concentrations, if you use like smaller intervals between the concentrations, it will become more accurate. Of course, there is the usual way for increasing the accuracy, which is repeat the experiment and calculate the mean. Also, one improvement that can work in like most of the questions, that these steps, they tell you to like do the experiment for all the concentrations all at the same time. So to improve it, you can use like prepare the experiment for each concentration at a separate time and do it separately. A student used the same procedure to compare the concentration of sugars in 3 vegetables: carrot, potato, and an onion. State one variable that needs to be standardized in the procedure. Of course, for different vegetables, the size or like the mass should be the same. Suggest how the student could extend this investigation to estimate the concentration of starch in a vegetable extract. So the tricky part here is that the examiner wants you to add the solution used to test for starch, which is the iodine solution. So to test for the concentration of starch in a vegetable extract, use at least 5 different starch solutions. Starch concentration, sorry. then test it using iodine solution. The faster so you can explain to him that they can use the speed for color change to reach the endpoint or the intensity of the color. For example, if it's a darker black, the iodine becomes a very dark black, then the starch content is high. But if the color changes barely noticeable from brown to like uh, just a darker brown, then the starch content is very low. For B, bananas produce ethylene gas which causes them to ripen. The production of ethylene gas continues after the bananas are removed from the plant, harvested. The ethylene gas decreases the post-harvest life of the bananas. The post-harvest life is the time after harvesting when the bananas are suitable to eat. Potassium manganate 7 can be used to increase the post-harvest life of the bananas by oxidizing the ethylene gas to form water and carbon dioxide. An experiment was carried out to determine the effect of different quantities of potassium manganate 7 on the post-harvest life of bananas. The results are shown in table 1.3. So these are the results. Of course, the left side is the independent variable, the right side is the dependent. So the left side is on the x-axis, then the right side is on the y-axis. To the table, the x-axis starts at 0 and ends at 8. You have 1, 2, 3, 4 divisions. Of course, you have to start at 0. So 0, 2, 4, 6, 8. Yeah, you can do it like that. So 0, 2, 4, 6, 8. It will be in the range, the minimum and the maximum. And of course, don't forget to label it. Mass of potassium manganate 7 in grams. Then for the y-axis, it starts at 9.30 and ends at the highest. So here the highest is 13.65. And we have 1, 2, 3, 4, and 5. You are not forced to start with 0. So for example, you can start at 9, 10, 11, 12, 13, and 14. Yeah. You can start at 9.0 here. So the first point would be at 0 and 9.3. More like there. Then to 11.525. 4 and 12.60 or 60, 6 and 13.65, then 8 decreases again at 11.45. Then you should connect the dots with a straight line using the ruler from point to point. Use your graph in figure 1.1 to predict the post-harvest life of bananas if the mass of potassium manganate 8 is 6.8 grams. So to find 6.8, this is 7 and 6.8 is right here. Then you will extend the line upwards and it's a dotted line. Then to the left. All of this, of course, is done by a pencil, HP pencil. I'm just using different colors for educational purposes. So here is 12.5, 6, and 12.7. It's a little bit above it, so you can, for example, write 12.73. And of course, labeling the y-axis, mean post-harvest life in days. Suggest why the post-harvest life of bananas decreases when more than 6 grams of potassium manganate is used. So for this question, it will be sometimes it will be given to you in this paragraph, which indicates that when potassium manganate is used, it oxidizes the ethylene gas to form water and carbon dioxide. So of course, you can write that water and carbon dioxide ruins the banana, and also that potassium manganate is toxic and affects the flavor of the banana. That's why the bananas decrease, the life of the bananas decrease. For example, that's it for question 1. Now for question 2, L1 is a slide of a stained transverse section through a plant root. Draw a large plan diagram of the whole section L1. Use a sharp pencil. And then use one ruled label line and label to identify the endodermis. So when you look under the microscope, it will look something like this. You might get like a perfectly circular one, but Then it's double lined. But then the part in the middle should be like also when you look here, it's perfectly a circle. So as much as you can, and the middle part is going to be triple lined. Then it's like a six-sided star shape in the middle. Something like that. Okay. So for the labeling part, it just says to identify the endodermis, which is this part. But for further explanation, because you might get to label and identify any other thing, this will be the epidermis. And this part is the cortex. The inner part is the pericycle. Then this part is the phloem, and the out innermost part is the xylem. And of course, that's the endodermis. Then observe the epidermis of the root on L1 and the layer of cells beneath. Select a group of 4 adjacent cells. This group must include 2 cells from the epidermis and 2 cells from below the epidermis. Each cell must touch at least 2 of the other cells. Each cell must touch at least 2 of the other. Make a large drawing of this group of 4 cells. Use one rule, label line, and label to identify the cell wall of one epidermis cell. So this is a magnified part. It's not very visible here, but you can zoom in the microscope. And for example, this is the epidermis. So you can draw 2 big parts from the epidermis. For example, these connected parts and 2 smaller parts under it. One. They are double-lined. Pasted. Then two smaller parts under it. Then to label one cell wall, just take this part. For this figure 2.1 is a photomicrograph of a stained transverse section through a different plant. Identify three observable differences other than the color between the section on L1 and the section in figure 2.1. Record these observable differences in table 2.1. So the first feature can be the shape. Of course, L1 is not circular at all. It's like crooked and wavy is the word. Wavy. And figure 2.1 is circular. Then for the vascular bundle, for here the vascular bundles are not in the middle. The vascular bundles are scattered around the cell, but in this figure the vascular bundle is right in the middle. So please bundle figure 2.1 in L1 it's in the center, but in figure 2.1 around the edges. Then of course the number of the vascular bundles there is more than one here, many of them, and right here is it's only one. Of course, if it's white like this part under the microscope, that means this part is filled with air. There is nothing. And in this photomicrograph, there is nothing, like there is no air in the middle. So also you can add the part here. You can put more than 3, because if there is one wrong, air space, then in L1 it's not present, and present in Fig 2.1 right here. For the last question in the paper, Figure 2.2 is the same photomicrograph as shown in Figure 2.1, and use the scale bar on Figure 2.2. This is the scale bar. On Figure 2.2 and the line AB to calculate the actual diameter of the section in Figure 2.2. Show your working including units. Then you will take your ruler on the paper and place it right here, like on this scale bar, and check how many centimeters it is. For example, I got 2 centimeters. So on the ruler, 2 centimeters are equal to 525 micrometers. Then you will take your ruler and place it on AB, starting from here to B, and then calculate the distance of this line. For example, you might get it as 7.4 centimeters. So 7.4 centimeters. Then you should find the actual diameter by, for example, if you write it like this, I use the method of cross multiplication. So it's going to be x, which is the actual diameter, is equal to 7.4 times 525 over 2. If you place this in the calculator, you will get the answer as 1942.5 micrometers. So the actual diameter is 1942.5 micrometers. To make it easier, you can multiply it by 10 to the power of -3, or divide it by 1000. That's to convert it to millimeters. So you will get it as 1.9425 millimeters. For example, to 3 significant figures, which is going to be 1.94 millimeters. That's for the last question, and thank you.